Today we'll start another problem that is known as the knapsack problem. Here there are two versions of the knapsack problem, and there are two methods also, two separate methods for two problems. So this is the outline. So now greedy algorithm, I have already stated that greedy algorithm is based on local optima. Means you will take decision based on your local optima. There is no guarantee that local optima will lead the global optima. So in some cases you may see that your local optima choice can really give the global optima, and in that case you have to prove it. But in some other cases you will see that local optima will not give the optimal solution. Also you have already seen that greedy choice.
Sir,
There are
sir, sir, sir.
tell me.
Yesterday we had left the optimize like the scheduling problems halfway, sir. You said you will teach some more about it, sir. So will we continue? Won't we continue that, sir?
I'm not getting. Hello.
Sir, yesterday your battery was low, sir. So
No,
that's
that
why.
problem was finished.
Okay,
I
sir. Okay,
I
sir.
thought. Okay. So anyway, so here you see the greedy algorithm. So greedy algorithm is an optimization problem. Okay, it makes a choice based at the moment, means local. Okay, this is based on the local optima, and it gives the now final output is an optimal solution. But you have to prove if it is optimal. That I have already stated that greedy algorithm does not always yield the optimal solution. In some cases, for some problem you will get, and in other cases you may not get the optimal solution. But please remember, I don't know whether this time in during online classes we will be able to we will get the time or not. That approximations solutions are also there. In approximation problem solving, the greedy algorithm also helps. Anyway, now what is the knapsack problem? Suppose you have a knapsack, means bag. Okay, large knapsack. So say this is the knapsack. Its capacity is 4. Its capacity is 4. Knapsack capacity is 4. And now there are three objects A, B, C, and the weight of the objects are given. So it's 2 pound, 2 pound, 3 pound, and this is the cost of the item A, $100, $2 to $10, and it is $120. Now what you have to do, you have to uh, fill up this knapsack using these objects so that you can profit as much as you can. That means your profit should be maximized. See, if you take 2 pound of this, means complete object A, then you will gain a profit $100. But if you take half of this object, you will get $50 profit. So you have to keep the objects whatever you wish, and your profits should be maximized. But please remember, the knapsack has capacity 4. That means, for example, here
Sorry.
you cannot put all the objects 2 pound, 2 pound, 4 pound plus 3 pound, 7 pound. It's not possible to keep all these objects here because it will exceed the capacity. Someone was asking something. Hello. Okay. So fractional knapsack, in there are two versions. Means if you can take a fraction of the objects, say I told you na half. If you take half of the objects, or say 1/3 of the objects, that is called fractional knapsack. And another problem is 0-1 knapsack problem that we will study later. So we can take fraction of an item. So say here you see this is the knapsack. Okay, this is the knapsack. Entire knapsack is this. Now what is the weight? 2 pound, 2 pound, 4 pound. Okay, and I have taken 100 here, and you see in this case, what is the, for 3 pound it is 120. So 1 pound it is 40. So for 2 pound it is 80. Clear? So this is the solution. Now 0-1 knapsack problems means this is the different issue. Here you will either completely accept the object, take the object, or you will completely reject the object. That's why it is called 0 or 1. No fractions is allowed. Say here in this case, for example, uh, you see, if I take both the objects A and B, 2 pound plus 2 pound, 4 pound in the 0 1 F6, then profit will be 110. But if you take instead of suppose you are not completely filling the knapsacks, but you are taking C, only C, then the profit will be 120. 3 pound, okay, 1 pound is see, this is vacant, this portion is vacant. Okay, so this is the 2 point. Please remember, 0 1 knapsack problem cannot be solved using any greedy idea. Okay, dynamic programming will help us to solve 0 1 knapsack problem. Dynamic programming we will learn later, and fractional knapsacks problem can be solved using greedy strategy. So what are the so how can I state the formally the problem? Formal definition is that given k means knapsack capacity k and a set of n items, their weights are w1 w2 dot 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 wn, and their values are v1 v2 v3 dot 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 vn. Now we have to find out a fractions of for each objects. Xi means x1 x2 x3. So for this x1, for this x2, in this way xn. Okay, so where each xi varies from 0 to 1. 1 means complete, 0 means nothing, and fraction means 0 point something. So that the sum, you see, the sum of the weights should fulfill this criteria, that should be less than equal to k. And what is the objective? Objective is to maximize this thing, the profit earned. What is the profit? You see, if I take the entire objects, I am getting v1 for the object 1. So if I take xi fraction, so I will get xi into vi. And in this case, you have to add all the profits of n items, and it is to be maximized. Okay, this is the problem. Now what will be the greedy algorithm? In this case, greedy algorithm for the knapsack problem is that sort the items
Sir,
by
could you explain the last part once more, sir? The last part will be just, sir.
this part.
Yes, sir.
Which one? This one or this one?
Sir, the second one, the maximized one, sir.
Maximize one means you have to maximize the profit. So what is the profit? See, profit is,
The
see, if you
V1.
v1, if you take entire object, full object of 1. Okay, this is object 1, this is object 2, so object 2 v2. Now if you take x1, x1 fraction, x1 is the fraction. So if x1 value is 1, then its value is v1. If x1 value is 0, that means you are not accepting, so its value is 0. x1, so if you take half of the objects, its value will be v1 by 2. If x1 is half, so
Sir.
you see, therefore the profit is what? The profit is actually x1 v1 plus x2 v2 plus x3 v3, in this way xn vn.
Yes,
That
sir.
I have to maximize with the constant this.
Yes, sir.
Now here you see one thing for uh, fractional knapsack problem. You see, if this is the capacity of the bag, okay, knapsacks, then fractional means you can take a fraction of the object. So what do you think? Will you fill up, means to get the optimal solution, will you fill up the entire knapsack, or there may be some empty space also in case of fractional knapsack problem?
So there might be empty space, sir.
No, because you see, I am allowed to take a fraction of an object. Suppose, okay, you are giving some optimal solution with some space. What I will do, if some space is there, I can take any object which are remaining also. I will, if I take them, I am sure the profit will not be decreased. Are you getting? Profit will not be decreased.
Yes, yes, sir.
So why should I not take? So in this case, you will see always the knapsack is always filled. Okay. See, generally what happens, I am saying that W1 plus W2 plus W3 plus Wn, this value must be greater than K. Otherwise, no meaning. If the sum of the weights of all the object is less than K, the easy solution, you take all the objects completely. So generally, this is given. So that you have to take these, and whether I should take this object or this object. Anyway, so I will fill up the knapsacks, since the profit will not be decreased. But in case of 0 1 knapsack problem, the knapsack may be vacant. Okay, because suppose you have obtained some solution. Now once you want to, there is some space, and if you would like to take another item, then it will exceed the capacity of the knapsack, because you are bound to take the complete objects. You are not allowed to take fraction. So you check it. Sort the items decreasing value per pound, means you have to find out the value by weight ratio. Okay, this ratio you have to find out that value by weight, and you sort the items, all the objects, according to this one. Say here A, B, C, D, 4 objects. Fine. It's 200 by 1, 240 by 3. So you see, this is the decreasing order. Fine. And if knapsack holds K equal to 5 pound, so objective will be 1 pound of these objects A, 3 pound of B, and 1 pound of C. Here you see, complete this A and B. For this you are taking complete objects. Okay, complete objects. And here fraction. Generally what happens, you will see that, see, you have sorted in the decreasing order, so automatically this is costly with respect to you, because value per weight. So automatically your objective will be you to take it as much as you can. Clear? So that means you will try to take maximum amount of A. So that's why you will take A complete, then maximum B, then if it is not possible, then a portion of this fraction. So that means xi values, that will be like this: 1 1 1 1 1, then some delta or epsilon, then all are remaining as 0. This is the object 1. I am saying object 1. This is the object 2. Which fractions? How much fractions are you taking? Clear? Is it clear what I am saying?
Yes, sir.
Only the last items, means that you will fill in the, that will take some fraction, and after that you will not take any other objects in case of fractional knapsacks problem. So you calculate the value per weight, Vi by Wi for all. Sort the items by decreasing this, and the corresponding value per pound, and weights are this, the Pi Wi. Let K be the current weight limit. In each iteration, what you will choose item I from the head of the unselected list. This is the list, na? Vi after sorting. And if K, whenever K will be greater than Wi, you will set Xi is equal to 1. That means you are taking complete, and you will reduce that see, once you take an object, the knapsack capacity will decrease. Please all do that. So you have to update the value of K also, and then consider the next item in the, and here you have to set K by Wi, that is a fraction of this. Then the algorithm terminates. This is the greedy solution. Okay.
Sir, could you go to the previous slide, sir? I just need to tally the A with the solution that we had. Yes, sir. Yes, sir. Okay, sir.
So whatever I told, this is the algorithm, and here you see the time complexity of the algorithm is determined mainly these steps: sorting, n log n. Otherwise, these are linear. Now, the question is that whatever you have generated, fine, prove that it is optimal. You are saying this is I am getting a solution, but you have to prove that this is the optimal. So observe that algorithm may take a fraction of an item. I have already stated this. This can be only the last selected items. And we claim that the total value for this set of item is optimal value. So correctness, proof of correctness. These are the n items, 1, 2, 3, up to n. And you assume that the items are sorted per weight objects. This is row 1, row 2. For each object, row is the, please remember, row I is Vi by Wi. And let the greedy solution, means our solution be this x1, x2, x3 up to xk. K objects has been, okay, means after k it is 0, means all the, I am not taking any other object. The xi indicates the fraction of the I taken. That I have also mentioned. All xi 1 except possibly for I equal to k. Now, suppose you are saying me that, sir, it is not optimal solution. So optimal solution is something else. Okay, fine. Give me. So this is the optimal solution, as said by you. To the next platform. Next, next, yi here indicates the fraction of the item I taken in O. Fraction of the item I taken in object O. Okay. Now knapsack must be full in both G and O. So that means sum total of the weight of the objects in our case and in optimal case is same. So you see that weight, sum total of the weight of all the objects in the selection in G and O is equal to K. Clear? Xi Wi and this is Yi Wi equal to K. Now you are saying this is the optimal and this is the, in our case, this is the greedy. So I am assuming, means I these two series will differ at some index. So where it will differ? So suppose I am assuming that the first I items, the first item I, where the two selections differ. That means up to 1, 2, means I minus 1 index. These two series are same. These two series differ only index I. Okay, at index I. Means xi is not equal to yi. So by definition, solution G takes a greater amount of I than solution O, that you have said, because that is optimal. Our case is not optimal. Now what we will show that we will change your schedule to me without losing. Means we will gain, or at least the profit will remain same. And we will say, and finally we will show you that your schedule, your solution O can be converted into our solution this. How? See, now you are saying, means I am saying that item I, where the first objects differ. First objects differ. So what we will do? So you take a greater amount of I, then solution O. Greater how? See, there are two schedules. Okay, this is the xi you are saying in our case, and this is the yi. Now in this, xi is not equal to yi. Now according to our algorithm, xi is larger than yi because we have sorted as per their this, and we are selecting this na. So xi is larger. So what we will do? We will take larger amount of I, then solution O. Means our solution of G takes a greater amount of I than O. So what is the difference? Let x be the difference, xi minus yi. Now, what we will do, we will show that a new solution O prime can be constructed from O. How? For j less than I, for j less than I, see, in this case, all the solutions will have index like this, yi prime. Means prime indicates O prime. So for all j less than I, means 1, 2, 3, dot, dot, up to I minus 1, that yj prime is equal to yj. I am not changing. And now we will set what? yi prime. Yi prime is equal to xi. Now in O, remove items of total xwi from items I plus 1 to n, resetting the yj value appropriately. That means here in optimal schedule, remove items of total weight xwi. What was x? X was equal to xi minus yi. Please remember in the last slide. Okay. And that multiplied by wi. So you are removing items of total weight, these, from item I plus 1 to n. That means what? Actually, see, actually I had, we, our solution had xi and their solution had yi. Yi is less than xi. Now what I am doing, I am, see, these schedules are same and there are some elements after these also. Now here you see what I will do, I will make these two equal. Xi is larger than yi. So how can I make it equal? I will put some element from here to here. That I am saying. That remove items of total weight xi minus wi from items I plus 1, this item, to n, resetting the yj prime appropriately. So this is always doable, means you can do it because this. This simple sum of all the fractions from I equal j equal to I to n in this case, and in that case are same. Now the total values of solution O prime is greater than or equal to the total value of the solution O, because I am maximizing the profit in each case, means at each index I. Here some profit is there. Whenever you are taking larger fraction of yi, then the profit is also increased. Okay, so the profit of O prime is greater than or equal to the total value of the solution O. Now since O is the largest, now O means optimal, is the largest possible solution and the value of O prime cannot be smaller than that of O. So O and O prime must be equal. Now this solution O prime is also optimal. Now if I repeat the next step, means I equal, then I plus 1, then I plus 2, I plus 3, dot dot. In this way, we will simply, actually what we will do, we will convert the solution O into G. Because please check it. I told you that this was xi in our schedule and this was yi. I am making these two in values equal, same. Okay. I am taking more amount of item here and I am converting this schedule O to O prime, where O prime and G prime becomes equal. So therefore this gives the optimal solution. G is the optimal. And greedy solution for 0 1 doesn't give the if you try to apply the 0 1 naps, means this problem, in case of 0 1 knapsack problem, it will not give the optimal solution always. In some case maybe, but not in always. But I have to make sure that it should give optimal solution in all, means in every each case. See, this is 303. So weight, so weight is value per weight, is this value per weight in this way. So what is the solution? Solution is item B plus C. K is 4. So if you collect B and C, you will gain profit, one 370. Okay, but if you take, means first this means it is 4. It's means 4. If you try to take this one, then it will be 3. So only 1 pound will be left, and in that it cannot take B or C because fractions are not allowed. So in that case, you will get a profit 300. So 0 1 knapsack problem does not give the optimal solution using the greedy method that you are applying in fractional knapsack problem. Okay, I will upload the uh, class video lecture as well as the slide also. Okay, so you tomorrow you have the exam. Questions are easy. You please uh, try to solve all these problems. There